Let's take a look at the quantum mechanics problems that you were asked to solve. Up at the top of the page, you have the equations that are relevant from the Chapter 7 quantum mechanics discussions based on the videos that you were asked to watch and the reading that you were asked to do. Question number 1 asks to calculate the frequency of a gamma ray with a wavelength of 2.55 times 10 to the negative 12 meters. In this equation, we're asked to calculate a frequency where we know the wavelength. What we know from our discussions is that we have an equation that gives us the relationship between wavelength and frequency, and that's this equation here. So when we plug in the speed of light for c, when we plug in the wavelength for lambda, we get 1.18 times 10 to the 20th inverse seconds for our frequency. In question number 2, we're told a 100-watt light bulb radiates energy at a rate of 100 joules per second. If all of the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? So in this question, we need to do a calculation about energy. So up at the top of our page, we have two energy equations. We have one equation that relates energy and frequency with Planck's constant, and we have a second equation that relates energy and wavelength using Planck's constant and the speed of light. In this case, because we know the wavelength, it's that second equation that we're going to be using. So in order to use this equation, we need Planck's constant, which is a constant. We need the speed of light, both of which are given to us in this information. We also need to make sure that we have our wavelength in units of meters. So the first thing that I did was to do that conversion from nanometers to meters, and I got 5.25 times 10 to the negative 7th meters. We know that the energy of one photon is 3.79 times 10 to the negative 19th joules. Now, this is really important because when we solve these energy equations, the energy that we calculate is the energy for one photon. One photon. So with the light bulb, we have energy that's being radiated at a rate of 100 joules per second. So if we know that the energy of one photon is 3.79 times 10 to the negative 19th joules, we can use that information to get the total number of photons from the light bulb. The other equation that you need to know is the one that you see here, and that is that the total energy is equal to the energy of one photon, which we calculate from those equations up above, times the number of photons. This equation was in the slide packet that you were asked to read. So that means if we use this equation, we know the total energy of the light bulb is 100 joules. We calculated that the energy of one photon was 3.79 times 10 to the negative 19th joules. And when we do that calculation, we get 2.64 times 10 to the 20th photons from the light bulb. Question number 3 says to calculate the wavelength of a 143-gram baseball traveling at 95 miles per hour. In order to do this problem, you will also need to know that 1 mile is equal to 1,609.34 meters. So for this problem, we're going to be looking at the de Broglie wavelength for a particle. So that's the equation here that says that our wavelength is going to be equal to Planck's constant divided by the mass of the object in kilograms times its velocity in units of meters per second. So for this problem, we are given the mass in units of grams, so we'll need to convert that to 0.143 kilograms. We're given the velocity of the baseball in units of miles per hour. So the first thing we need to do is a unit conversion from 95 miles per hour to 42 meters per second. From there, we can plug into the equation for Planck's constant. We can plug in for our mass in units of kilograms and our velocity in units of meters per second. Be sure you use parentheses for the denominator of that equation, and when you solve, you should get 1.1 times 10 to the negative 34th meters.